Hey, it's Zach, and today we're talking about fiber optics. They're really cool, so enjoy, and don't forget to like, comment, and subscribe. Fiber optic cables transmit data in the form of ones and zeros, usually light. Typically, infrared light is used. So how do fiber optic cables do this? In order to understand the how, we need to understand how light travels from one material to another. When light travels into another material, it bends in a process called refraction. When light travels into a material that causes it to slow down, it bends towards the normal. An example of this is when light travels from air to glass. However, when light travels into a material that causes it to speed up, it bends away from the normal. An example of this is when light goes into air from glass. So how do optical fibers use the principle of refraction to work? When light tries to travel into a material that causes it to speed up, it is possible for the light to bend to the point that it travels back into the material. This phenomenon is called total internal reflection. Fiber optics use total internal reflection to transmit light from one location to another. Light propagated by total internal reflection will continue to zigzag down the length of a fiber. This leads to another question. How do engineers know when light will refract and when light will reflect by total internal reflection? The answer to this lies in something called the critical angle. When light strikes a material at an angle less than the critical angle, the light will refract. However, when light strikes at an angle greater than or equal to the critical angle, the light will reflect. Before we can calculate the critical angle, we need to go over another concept called the refractive index. The refractive index equals the speed of light in a vacuum divided by the speed of light in that particular medium. This index is used to quickly compare the speed of light in various materials. For example, light travels faster in a material with a refractive index of 1.15 than it does in a material with a refractive index of 1.32. The refractive index of each material is also used in an equation called Snell's Law that determines how light will refract when traveling from one material into another. The equation goes as follows. The index of refraction of the first material signed the angle that light is traveling through the first material equals the index of refraction of the second material signed the angle that light is traveling through the second material. More importantly, a variation of Snell's law can help you find the critical angle needed for total internal reflection to propel light through the fiber optic cable. The critical angle equals the inverse sine of the refractive index of the material the light intends to enter divided by the refractive index of the material the light started from. We have covered the physics that enable light to travel through fiber optic cables. Now we will cover how fiber optic cables use these principles to transmit data through its structure. At first glance, it seems like all fiber optic cables would need is a material with a higher refractive index than air for total internal reflection to occur, and therefore for light to travel through the cable. However, this would leave the cable prone to damage and be very inefficient. To be viable, fiber optic cable has a core that transmits light, cladding made of a lower refractive index material than the core that enables total internal reflection, and a plastic jacket that protects the cable from damage. The refractive index difference between the core and cladding is not very much. For example, the core will have a refractive index of 1.48 and the cladding will have a refractive index of 1.46. This is done to increase the critical angle required for total internal reflection to occur. The less paths of light that can reflect, the more efficient the cable is at transmitting light and therefore data. The why behind this will be discussed later in the presentation. The core and cladding are typically made of silica glass. Dopants, which are atomic element impurities, are added to the silica glass to create the slight refractive index differences between the core and cladding materials. The core and cladding can also be made of plastic, but while they are more flexible and cheaper than their glass counterparts, they are so inefficient that they are typically only used in educational kits or very short transmissions. By this point, you may be wondering why glass is used because of how brittle it is. I know I was when initially researching this topic. However, glass by itself is not brittle. Rather, the normal manufacturing process produces microscopic scratches on the glass that cause it to be brittle. Fiber optic cable is manufactured in a way that the glass is created without scratches. We have talked about light principles and how fiber optics use those principles to transmit data. Now let's briefly discuss why you would use fiber optic cable instead of copper cable. Optical fiber, unlike copper cables, does not radiate or pick up electromagnetic radiation. This means that they will not emit electromagnetic interference that can disrupt electrical equipment or signals, and the signal transmitted by the fiber optic cable will not be distorted by electromagnetic interference. Fiber optics also transmit data at faster rates than copper wire because the speed of light is always greater than the speed of electrons. Lastly, fiber optic cable has relatively low attenuation or losses compared to copper wiring. A discussion about fiber optics would be incomplete without mentioning the two main types of fiber optic cable. There are multimode cable and single mode cable. A mode is one path of light. Based on this definition, multimode cable allows multiple paths of light, while single mode cable only allows one path of light. What does this mean concerning the functionality of multimode and single mode cable? Data is transferred digitally in optical fiber. This means that data is transferred in the form of ones and zeros. When the light is on, a 1 is transmitted, while a 0 is transmitted when the light is off. The ones and zeros form a crisp square wave. In multimode fiber, multiple modes or paths of light enter the cable for each pulse of light that represents a 1. This is not an issue for relatively short distances, but becomes an issue over longer distances. When paths of light enter the fiber at different angles, they arrive at the final destination at different times because some waves travel through the cable quickly and others travel through the cable more slowly. When the light paths differ enough, the crisp square wave at the beginning of the transmission spreads and starts to look like the top half of a sine wave. Eventually, these distorted square waves overlap and start to merge. When they merge, information becomes lost. This phenomenon is called modal dispersion. This can be avoided by using single mode fiber. Single mode fiber is small enough that it only allows one path of light to travel per light pulse. By doing this, modal dispersion cannot occur and the efficiency of light travel increases. So why use multimode fiber if single mode fiber transmits light better? The answer is cost. Single mode fiber costs about 4 times more than multimode fiber. Therefore, multimode fiber is good for applications that don't require light to travel great distances, such as in data centers or local area networks, also known as LAN. However, for long-distance applications, such as transmitting internet data or text messages, single-mode fiber is needed. How fiber optics are used in these applications are beyond the scope of this video, but Learn Engineering, a YouTube channel, has a couple great videos on this subject. In summary, we have discussed how fiber optics use the principles of light to transmit data. When light travels from a material with a higher refractive index into a material with a lower refractive index, it bends. However, depending on the materials and light angles involved, it is possible for light to travel back into the first material in a process called total internal reflection. Fiber optics use total internal reflection to transmit data in the form of light great distances. This is more efficiently done using single-mode fiber but for applications that don't require light to travel very far, multimode fiber is ideal because it costs less. Hey everyone, I hope you enjoyed this video, and don't forget to like, subscribe, and click on the notification button for more electronics videos.